Hi, I welcome you all to this session on elasticity, and taking you along on this journey is Dr. Yunus Jerusha, an Assistant Professor of Physics. Some of the most important properties which are useful on the industrial scale are physical properties which are quite intensive. We are looking at certain physical properties which are quite intensive in nature, such as hardness, ductility, and malleability. Some of our favorite eatables also exhibit material properties. Caramel, which we all chew upon, is quite stiff in nature. A chocolate bar is brittle, and after dinner mint is weak, and lollipops, due to their brittleness, get completely destroyed on absorbing energy. Materials can be classified as perfectly elastic and perfectly plastic depending on their elastic nature. What is a perfectly elastic material? Here, the mattress undergoes a deformation when a pressure is applied, and later, when the pressure is removed, the mattress comes back to its original size and shape. This could be cited as an example for a perfectly elastic material. For a perfectly plastic material, we have a rod which is metallic in nature, and it is subjected to an extremely high amount of stress and undergoes deformation, and it can never come back to its original size or shape even after the removal of this deformative force. What is meant by the term elasticity? Let's try to understand this by means of an animation. A spring is elongated, and later, after it is let off, it comes back to its original shape and size. If a material is subjected to an external force, it creates a deformation in molecular structure of that material. The physical process wherein a material returns to its original shape after removal of the deforming force is called as elasticity. Also, it is the property by which a material can withstand change in its size or shape when an external force is acting on it and returns to its original state after the elimination of the deforming force. Hope this would have given you an idea of what is elasticity. We have just seen how a body undergoes deformation. Deformation occurs when a body is subjected to an external force or stress. Stress is defined as the restoring force per unit area which brings back the body to its original state from the deformed state. As long as no permanent change is produced in the body, the restoring force is equal to the force applied. Stress, therefore, is a ratio between the force applied to the area with a unit Newton per meter square or Pascal. Stress can be classified into two types: normal stress and tangential stress. Normal stress is when the force is applied perpendicular to the surface of the body, and tangential stress occurs when the force is applied along the surface of the body. The tangential stress is also called as shear or shearing stress. Depending on where the stress is applied, we have a further classification of the normal stress as longitudinal stress, where we have compressive and tensile stress. There is another type of stress also. It is called as the bulk stress. Tensile stress is when the force tries to pull the body in an external direction away from the body. Compressive stress, on the other hand, occurs when the force is applied inward or internal to the body. Strain is the outcome of the applied stress on a body. It is defined by the ratio of the change in dimension to the original dimension. Relative change in the configuration due to the application of deforming forces is what is called as strain. Mathematically, strain is the ratio of the change in dimension to the original dimension, and since we have dimension on the numerator as well as in the denominator, strain has no unit. Strain is classified into 4 types, the first being longitudinal strain. Longitudinal strain is defined as the ratio of the change in length to the original length, and it is given by the formula small l by capital L. The second type of strain is the bulk strain, and it is defined as the ratio of the change in volume to the original volume. The formula being small v divided by capital V. Third type of strain is the shear or shearing strain. It is the angular deformation produced on the body due to the application of an external tangential force on it, and it is given by the ratio between the displacement and the edge length. The formula for it is theta is equal to small l by capital L. Finally, we have the lateral strain, which is the ratio of the change in diameter to the original diameter, and it is denoted by beta, which is given by small d divided by capital D. Consider a wire of length L fixed at one end and free at the other end. The free end is loaded, and therefore the wire undergoes an elongation by a small length L. The wire also undergoes a change in diameter. The original diameter is capital D, and the change in diameter is given by small d. Therefore, the new diameter is d minus small d. We can therefore say that the wire undergoes a change in its length as well as a change in its diameter. The change in length is given by the longitudinal strain, and the change in diameter is given by the lateral strain. These two strains are related by a ratio called as the Poisson's ratio. It is a ratio between the lateral strain denoted by beta per unit stress to the longitudinal strain alpha per unit stress. So, in this formula which we see here, it is the lateral strain beta divided by the longitudinal strain alpha equal to small d by capital D divided by small l by capital L, where small d stands for the change in diameter, capital D the original diameter, small l stands for the change in length, capital L standing for the original length. We now move on to relate stress and strain by means of a law called as the Hooke's law. Have a look at this diagram. In this diagram, the first picture which we see here is a spring which is completely unloaded. Therefore, there is no change in its shape or size. On subjecting the free end of the spring to a tensile force F, it undergoes a displacement small x. Let us now apply a load twice that of the original force. Therefore, there is a corresponding displacement which is equal to 2x. So what we observe here is that as force increases, there is a linear displacement also occurring in a proportional manner. Therefore, F can be said to be proportional to the displacement, and mathematically we have F to be equal to kx. It is given in the form of a statement: for relatively small deformations of an object, the displacement or size of the deformation is directly proportional to the deforming force or load, given by F is equal to kx, where F is the tensile force applied and x is the displacement undergone by the object, and k stands for the spring constant or the restoring force constant. Under these conditions, the object returns to its original shape and size upon removal of the load. This is a classical form of the Hooke's law. Now, for a refined and revised version of the Hooke's law, the maximum value of the stress within which a body completely recovers its original shape or size when the deforming forces are removed is known as the elastic limit of the body. Within the elastic limit, the ratio of the stress to the strain is a constant. This proportionality constant is known as the modulus of elasticity of the material. We write it in the form of a ratio of stress and strain, and this ratio is a constant. When tensile forces are applied to a body, it is subjected to a stress and thereby undergoes a strain. A linear relationship is followed between stress and strain till the proportional limit and obeys Hooke's law. Beyond that, it approaches the elastic limit till which it maintains its elasticity. Hooke's law, as we know, is a relationship between stress and strain. This linearity between stress and strain is plotted for various materials which are shown here. We have steel having the highest slope and therefore having the highest modulus of elasticity of 10 power 11. And on the decreasing scale, we have rubber, various types of gels and biological tissues. We see rubber here, which we generally say is elastic in nature, to have a low modulus of elasticity at around 10 power 6 Pascal. Depending on the three types of strain which we've seen, we have accordingly three types of the moduli of elasticity. The first, Young's modulus. second, bulk modulus, and thirdly, the rigidity modulus. We are going to see each of these in detail in the forthcoming slides. Let us consider a wire of length L and area of cross section A. The area of cross section is present here. Let one end of the wire be fixed and let the other end be free and loaded with a mass M. The wire, on being loaded, undergoes an elongation and is stretched by a length small l. Therefore, small l is a change in length due to the action of the tensile force F. On removal of the load, the wire undergoes a compressive stress and tries to go back to its original length. We relate this change in length and the original length by means of the Young's modulus of elasticity. It is the ratio of the longitudinal or tensile stress to the longitudinal strain. The longitudinal stress is given by the ratio between F and A, where F is the restoring force and A is the area of cross section. The longitudinal strain is given by the change in length small l divided by the original length capital L. Therefore, Young's modulus of elasticity denoted by capital Y is given as F by A divided by L by L, and putting it all together we have F into capital L divided by A into small l with the units Pascal or Newton per meter square. Consider a solid cube whose lower face ABCD is fixed to the base, while the upper face PQRS is subjected to a tangential force. The result is the cube gets deformed to that of a rhombus. The lines joining the two faces are shifted by a small angle phi. Phi here is called as the shearing strain or the angle of shear. If L is the length of the edge on which the tangential force is applied, there is a relative displacement small l of this edge. We now define what is called as a shearing strain. It is the ratio of the relative displacement between the two layers. The layers which are mentioned here are ABCD, the lower face, and the upper layer is PQRS, in the direction of the stress to the distance measured perpendicular to the layers, which is capital L. The rigidity modulus is defined as the ratio of the shearing stress to the shearing strain. It is given by this formula: eta is equal to the ratio between the shearing or tangential stress to the shearing or tangential strain. Substituting for the shearing stress as F by A and the corresponding shearing strain by tan phi, where phi is very small and approximated to phi, we have the rigidity modulus to be finally equal to Fl by Al, and the unit given is Pascal or Newton per meter square. Let V be the volume of a body with an area of cross section A. Let three equal forces act in the three mutually perpendicular directions as shown in the figure. Let small v be the change in volume due to the action of the forces. Then, the bulk modulus of elasticity of the body is given by the ratio of the bulk stress to the bulk strain. The bulk stress is given by the ratio of the restoring force F to the area of cross section with the units Pascal or Newton per meter square, and the corresponding bulk strain is given by the change in volume small v to the original volume capital V. Therefore, the bulk modulus is finally given by Fv divided by Av with the units Pascal or Newton per meter square. Materials can be classified as strong or weak materials depending on the amount of stress they can withstand as well as the strain undergone by them. We have two materials here, one to which we apply a force F on a small area of cross section. Therefore, we say it is subjected to a large amount of stress. But if the same force is applied to a large area of cross section, we say that the material is subjected to a small amount of stress. Looking at the next material here, a force is applied and the material undergoes a large amount of deformation. Therefore, we say that the material has undergone a large strain. On the other hand, a material is there to which a force is applied, but the deformation undergone by the material is quite small. Therefore, we say the material has undergone a small strain. Various combinations of stress and strain in the ratio of stress to strain tells us whether the material is strong or weak. If the ratio is large, we call that material to be a strong material, and if the ratio value is small, we call the material to be a weak material. Let us consider a body which is subjected to an uniformly increasing stress. Due to the application of the stress, the change in dimension of the body takes place and a strain is developed. If we plot a graph between stress and strain, we get a curve as shown in the figure, and it is called as a stress-strain diagram. From the figure, it is found that the body obeys Hooke's law up to the region OA. As soon as the maximum elastic limit or yield point B is reached, the strain increases rapidly than the stress. At this stage, the body remains partly elastic and partly plastic. This is a region BC where we have partial elastic as well as partial plastic behavior. Now, even if a small external force is applied, the body will take a new path CD and remains as plastic, called as a plastic range, where point D is called as the ultimate tensile strength. After this, the body will not come back to its original state and the body acquires a permanent residual strain and it breaks down at a point called as the breaking stress or fracture point, indicated by the point E. This figure clearly tells us which region is elastic and which region is plastic. point B, which is the elastic limit or yield point, the body remains elastic in nature given by this blue shaded region, and the body becomes completely plastic beyond the elastic limit or yield point. The set of curves shown here is the ultimate result of a stress-strain diagram. Therefore, the stress-strain diagram is used to categorize materials into ductile, brittle or plastic. For ductile materials, the region between the elastic limit and the fracture point is quite large. Whereas for the case of a brittle material, the yield point coincides with the breaking point. And for the case of a plastic material, the stress-strain diagram runs parallel to the strain axis beyond the yield point. And finally, for the case of a strong material which is not ductile, the curve breaks off at the elastic limit. It is found that some of the bodies around us lose their elastic property within the elastic limit due to elastic fatigue. Other than elastic fatigue, some materials change their elasticity due to various other factors which are listed here. One is stress. Stress causes the elasticity of a material to either increase or decrease. Repeated cycles of stress lead to a decrease in the elasticity of a material. Therefore, the working stress should be less than that of the ultimate tensile stress, and if it exceeds the ultimate tensile strength, it leads to the necking and fracture of the body. Secondly, the elastic modulus is affected by temperature. Generally, elasticity increases with a decrease in temperature and vice versa. In carbon filament, the carbon filament becomes plastic with a rise in temperature, and lead increases in its elastic nature at low temperatures. Whereas for the case of invar, there is no change whatever be the temperature. The next factor which affects the elastic modulus is the impurities. Impurities affect the elastic modulus in a varied manner. The increase and decrease of elasticity depends on the type of impurity which is added to it. When potassium is added to gold, the elastic property of gold increases. When carbon is added to molten iron, the elastic property of iron decreases, provided the carbon content should be more than 1% in iron. The next factor which affects the elastic modulus is the crystalline nature. Elasticity changes with the type of crystals present. For a single crystal, the elasticity is more, whereas for a polycrystal, there is a decrease in the elasticity. Annealing. Annealing is another factor which affects the elastic modulus. Annealing is a process by which the material is heated to a very high temperature and then slowly cooled. Usually, this process is adopted for materials to increase the softness and ductility, but if annealing is made to a material, it results in the formation of large grains which ultimately reduces the elastic property of the material. Finally, material processing. Material processing can happen either by hammering or rolling, which leads to finer grains being created in the material, and fine grains lead to an increase in the elastic property of the material. We came across a term called as tensile strength in the previous few slides. Let us see what it actually is. Tensile strength is the maximum force required to fracture a material. It is the maximum point represented in the stress-strain diagram, and also it is a measure of ductility of the materials. And always for a material to be elastic, the working stress has to be less than the tensile strength. If it's the other way around, necking and fracture occur in the material. There are various factors which affect the tensile strength. The first one being temperature. As temperature increases, there is a decrease in the tensile strength and vice versa. Heat treatment also leads to an increase of the tensile strength, along with an increase of toughness as well as shock resistance. Impurities too affect the tensile strength. We have an increase in the tensile strength due to the addition of impurities. Finally, grain size also affects the tensile strength. Finer grains lead to a higher value of the tensile strength of the material. We've seen in this session various terms which are acquainted with the elasticity of materials such as stress, strain, the relationship between stress and strain, and how various factors affect the elasticity of a material. Thank you for your patient listening.